In this video, I am going to walk you through the calculations on the oxidation of steel wool. You should have watched the video of the experiment by now, where we take a piece of steel wool and we touch it with a 9-volt battery and it starts to kind of light and basically burns in oxygen in air, and it forms an iron oxide. Steel wool is mainly made out of iron. We're going to ignore the little bit that it isn't, and assume that all the steel wool, so all of the iron is coming in the steel wool, is the same as the mass of the steel wool. The data to fill this table is going to come from pictures that are found in the lab instructions web page. Okay. Look for the little table that has images, and you're going to click on each image and it's going to pull up a picture of a scale with a mass in grams. There's only one mass for the empty crucible because this is the same for all 3 trials, and therefore there's only one picture, so go ahead and put it for all 3. Then there's going to be 3 different pictures for different trials of crucible plus steel wool, and enter those values in the second row here. And then to figure out the mass of steel wool alone, you have the crucible plus steel wool, and you have the mass of the empty crucible, so do the subtraction of both to get that. Then when we get to the mass of crucible and oxidized steel wool, you'll have 3 other pictures that you can look and get the mass from those. Then to get the mass of added oxygen, you're going to take the mass of the crucible and oxidized steel wool minus the mass of the crucible and steel wool alone. Now, what is going to happen, or what does happen, when we burn steel wool in air? It reacts with the iron in steel wool, reacts with the oxygen, and it forms an iron oxide. So instead of just plain iron in the steel wool, we now have iron oxide, and oxygen is added to the iron, and therefore the mass of the oxidized steel wool is going to be larger than just of that steel wool. And the extra mass obviously is coming from the oxygen. So that's why you do the subtraction of this row here with that row to get the mass of the oxygen that is added to the steel wool. Now the first question in the lab instruction or the lab report says calculate the mass of steel wool for each trial, and you do that by subtracting these 2. Assume that this is the mass of the iron as well, and I already mentioned that it's mostly iron. We're going to ignore the other parts that aren't. Calculate the moles of iron in each trial. And by now we should know how to calculate moles once we have the mass of the iron. We can go to the periodic table, figure out what the molar mass of iron is, and calculate the moles. Take the mass of iron, divide by the molar mass to get the moles of iron. Then once you get number 2 done, calculate the average number of moles of iron. Just take the 3 trials and calculate an average of those 3 values from part 2. And that's going to be what you write down for part 3. Please make sure that you follow the units, and all of these are supposed to have units with them. So the mass will be obviously in grams, the moles will be moles, and number 3, since it's the average number, it will also be moles. Then part 4 says calculate the mass of oxygen in each trial. We already talked about how we calculate the mass of oxygen, so all you have to do here is show me one calculation, one subtraction, where you take mass of crucible and oxidized steel wool minus mass of crucible and steel wool to get the mass of oxygen. And then you can write the other 2 answers. You don't have to show me all 3 subtractions necessarily. Then you do the same thing for moles of oxygen as we did for moles of iron. The only difference is that we're using a different molar mass because we have a different compound. So oxygen is 16, whereas iron is 50, well, in the 50s. I don't remember now off the top of my head. So they'll have different molar masses because they're different elements. And when we find the moles of each, we have to use the correct molar mass. So iron is 55.85, where oxygen is 16. Then, when we calculate the average moles of oxygen, you will take the 3 trials and find an average of those 3 values. Lastly, using the values in answers 3 and 6, determine the empirical formula. Now, you might get slightly different ratios, right? What we're going to try to do, you can do the larger number divided by the smaller number. This, it may work well or it may not. It might be easier if you just divide the moles of iron to the moles of oxygen. And there will not necessarily be whole numbers, perfect numbers, okay? But if they are close to 1, let's say you get 0.95 or even 0.8, you can round it to 1. Or if you get 1.8, then round it to 2, etc., etc. But if you get something in between, and we'll talk about it here, like 0.5, then don't round, just use this scenario over here. There's the 3 possible scenarios. So if I take the moles of iron, which I found in part 3, and divided by the average moles of oxygen, which I found in part 6, if I get a 1-to-1 ratio, so if that division comes out to be about 1, 0.9, 0.8, I can round, etc. But if it does, then it's a 1-to-1 ratio, so that means I have 1 mole of iron for every mole of oxygen. And this will give me this empirical formula of FeO. Obviously, I don't write the subscripts of 1 because they're implied, but that's a 1-to-1 ratio. The second scenario, I can have, if I take the moles of iron for part 3 and divide it by the moles of oxygen in part 6, if I get a 2 or close to a 2, that means I have a 2-to-1 ratio. I have twice as many irons as I do oxygens. And if I get 1.8 or that kind of number, just round up a little bit, okay? Then the empirical formula becomes Fe2O1, and I don't write the 1. And this tells me that I have twice as many irons as I do oxygens. So Fe2O. The last scenario, if I do that division, is a 1-to-2 ratio. Or if that division comes out to be 0.5, so if it's 0.8 or 0.9, then round up to 1. But if it's closer to 0.5, then round to 0.5 and call it good. And the empirical formula then becomes FeO2, because then I have twice as many oxygens as I do irons. So those are your 3 different scenarios that we're going to use to determine the empirical formula of the compound that is formed when we burn or oxidize steel wool in air.